one example of integration of information across several pieces of the brain. That's all this is trying to point out to you, is that something as important as the cerebellum cannot function on its own. It requires information. So we look at the top. It says all fibers in the cerebellum are ipsilateral. That means that their information coming to the cerebellum does not cross over. May not have a big impact on you. If we had more time, I would do my best to make it impactful. We just don't have the time. The cerebellum is collecting information from one side, the same side that it is on. It doesn't cross over. Yes, Darielle? Okay. All right. The cerebellum receives input from the cerebral cortex. The cerebellum learns of the plan of the cerebral cortex. What does the cortex want to do? Signals from proprioceptors and visual and equilibrium pathways continuously inform the cerebellum of body's position and movements. If you're unfamiliar with the term proprioception, the body's joints and its skin know what the condition of stretch and location of different body parts. If I put this body part like here, I have stretch receptors here, I have them in the tendons, I have them in the muscle. This is all proprioceptive input that the cerebellum uses, okay? Visual input is important. We can't ignore the fact that the eyes are open and that they understand what's going on in front of them. And then equilibrium pathways, the vestibular input, okay? So the cerebellum gets the plan and then looks at where the body is and then calculates best way to complete the plan. Or if the plan isn't going according to the way it was intended, the cerebellum will make adjustments by telling the cerebrum to make alterations, okay? So pretty impressive. You have multiple areas of the brain working together at the same time. One of them being a little bit more, let's say, of a master controller by making some subtle adjustments when necessary. Okay. We'll take a break here in about 10 minutes. All right. I know you've been waiting for it. The second portion of the central nervous system is the spinal cord. The spinal cord is found at the foramen magnum, and then inferiorly it passes in the vertebral foramen until about the location of L1 or L2. This is something I did not know before taking a class like this. You thought that the spinal cord went all the way down to the end. But it actually terminates. It depends on the human being. It either terminates at L1 or at L2. And then it becomes a bunch of nerve roots that continue on in the vertebral foramen. Vertebral foramen, you may remember, is that opening in the vertebra between the body and the arch. Okay? All right? What does it do? Its primary job is to provide for communication to and from the brain. That's its primary job. Okay? So in that regard, it is a pathway, and you astute people who are here with me this morning know then to look for white matter in the spinal cord. When we have pathways, we get white matter. But then we see contains spinal reflex centers, and you'll be learning about these here today, either tonight on your own or here in the classroom. This requires a little bit of integration. This requires collecting up a sensory input, figuring out what to do with it, and then generating the right motor output. This is very much brain-like in a way. Integration we tend to associate with brain, okay? But it can occur at the spinal cord level, all right? We studied the protection of the brain, and those protections we saw for the brain are present in the spinal cord as well. Does it always protect the spinal cord from serious trauma? Absolutely not. But it works fairly well for most people for a lifetime. Terminates, you'll see this in a diagram, it's something called the conus medullaris That is, the spinal cord goes from being a cylindrical device to a tapered point. And then it has a bunch of nerve roots that come off. Okay? Since the meninges are present, they will continue to protect the nerve roots and to anchor the spinal cord in place. Just like the brain is not supposed to bang into the sides of the skull, the spinal cord is kind of held central in the vertebral foramen, and it should not bang side to side within the vertebral foramen. Okay? So there's a bony armor around it, and it's held in place more or less by meninges. Okay? We have to talk about this here, which we will. There is cerebral spinal fluid surrounding the spinal cord. It is found in the subarachnoid, like it is up around the brain. Okay? And they're showing these two things here. These are part of the meninges, and they, once again, anchor the cord in place, both vertically and horizontally. Filum terminale, denticulate ligaments. If you've been doing your reading, you bumped into these. This is longitudinal section of the cord. We see the brain up above, and there would be the location of the foramen magnum. We see that the cord continues through the cervical and thoracic areas, and then it tapers pretty dramatically right here in the lumbar area. This is L1, that one's L2, and we see that the cord in this specimen is tapering and ending right around L2. We do then see nerve roots that pass continually down, okay, in the same location. Now those are getting the name the cauda equina, the horsetail, okay, the horsetail. And those things are surrounded by meninges and protected just like the cord. What's the difference between the two? These are roots of nerves. They're not spinal cords with gray matter and white matter. These are all white matter roots. The spinal cord itself is structured in a different way. You can see here then that there are nerves that enter and exit the spinal cord all the way along. Okay? Up in here, there are 8 pairs of cervical spinal nerves that enter and exit. We have to say enter and exit because, in fact, sensory neurons enter the spinal cord on these nerves and motor neurons exit. So it is truly enter and exit. We can see then that in this area, the spinal nerves that enter and exit the cord are referred to as thoracic spinals. And we get down into here, and even though our spinal cord terminates, portions of the cord that are associated with lumbar spinal nerves continue. Okay, so the lumbar spinal portion of the cord is up here, but the roots continue and exit the cord along the lumbar vertebrae. We also get roots that exit the cord along the sacral vertebrae, if you want to call them vertebrae, and then along the coccyx as well. So there are groupings of spinal nerves based on the names of the bones: cervical, thoracic, lumbar, sacral, coxal. Okay? This is what the cord would look like in dissection, and you are seeing that the cord actually has an outer covering of white matter, different from cerebrum and cerebellum, right? Central white matter in cerebrum, cerebellum, outer gray matter. The cord has outer white matter with central gray, okay? There we're seeing the rootlets that eventually either join up and form a root of a spinal nerve, or a spinal nerve root will divide into them and enter the cord. You know what I'm saying? These little rootlets will join up and form a spinal nerve. If the portion of the nerve is coming to the cord, then the nerve will diverge many times and become these little roots and enter the cord. Okay? Not all that earth-shattering. You can see there meninges, just barely. Okay? If you've read about the denticulate ligaments, if you looked closely, you might find them in here as well, and they anchor the cord side to side. At any time, if you have questions, just ask. Now we can see a bit of a zoomed-in view, And we're not seeing the central gray matter, but we're seeing that cord and its meninges and the space that is created in the vertebral foramen. If you remember back in the lab, looking at those vertebrae, that little space was not that big. Depending upon the size of the vertebra, it would really be quite small, all right? So that thing is actually looking a lot bigger than it really is, all right? There is the conus medullaris. There is the termination of the spinal cord. Notice it doesn't just end, it tapers, and then there's all the nerve roots, okay, which are referred to as the cauda equina, the tail of the horse. Those nerve roots continue down and eventually join up and create spinal nerves. Yeah.
So that's the end of the spinal cord?
That's correct. That is it. So if you're going to be tested on this, then you'd say, oh, that's right around L1, L2. Okay? Now there is, I don't know, we'll see. Okay? If you do your count of vertebrae, remember we learned there were seven cervical, 12 thoracic, 5 lumbar, there were 5 basic sacral vertebrae. If you add all those up, and coccygeal, you'll get 30. And then there is one more pair of spinal nerves that comes right out of the foramen magnum. Okay, so there's considered 8 cervical spinal nerves. This is what the cord looks like in the vertebral column. This is, what kind of vertebra do we have here? Does it say it up there?
Cervical.
This is a cervical vertebra, very good, okay? There would be blood vessels in these openings. This is anterior, that's posterior. So this is a pretty small space. We see the cord with its gray matter. It has sort of a central H-looking thing of gray matter. And this is what I wanted to point out, is the space around the cord. We've already learned that there will be a pia that attaches to the cord, that there will be an arachnoid which will create a little space between the pia and the arachnoid for fluid to flow, okay? And then we've learned that there's kind of a tough dura, and the dura will literally surround the cord as its outermost layer, but then also surround and sheath spinal nerves as well. So the dura will go out and be continuous with the outermost covering of spinal nerve. Now perhaps the more interesting thing, which is this epidural fat and this epidural space, okay? If you've had a child and had an epidural, you know where I'm going with this thing, all right? The first thing is epidurals are given below L2, so we don't have cord in the way. We have nerve roots. But I did want to point out that what they will do, if you've been through it, you know, at a time when you probably don't want to sit up in bed bent over, you're asked to do this, and then a needle is placed in such a way that the needle reaches the epidural space. It doesn't penetrate the dura, it penetrates right into here. Now, they obviously don't go through bone. They bend you over so that they can get the needle between the bone, okay? Now, again, this would not be here. Instead, there would be nerve roots. They then remove the needle, leaving behind a cannula. And the cannula then is going to be attached to a pump, and then anesthetic can be pumped right into the epidural space. Okay? So it cannot be done up here. They don't put needles into the vertebral foramen if there's a spinal cord there. Okay? Now what does it do if you've been through it? There's a couple of you who have had children in the room. If you've had it, what it should do is greatly reduce pain without leading to a total loss of sensation. Is that what you experienced? Did anyone have it?
It's pretty accurate.
Okay. You should still have the ability to, let's say, push and get some feeling of that push without the extreme pain. Epidurals can be used for other kinds of procedures other than childbirth, labor and delivery. But if they really want to numb you down, then they're going to probably pass that needle into the space. They're going to penetrate through the dura. And they're going to then put anesthetic right on those nerve roots, again, below L2. And then you'll be total loss of feeling at all, complete feeling. So A spinal anesthetic would probably be good for like a knee replacement